Okay, so we will wrap up kind of this series of videos that are dealing with matrix vector products by specifying a couple of key properties that a matrix vector product satisfies. So if A is an m by n matrix, we have m rows and n columns in matrix A, and we have vector u and vector v that are in Rn, and C is denoting a scalar. The first property is telling us that if I take matrix A and I multiply it by the sum of vectors u and v, then that is equal to matrix A times vector u plus matrix A times vector v. So this is like a distributive type of law that we've seen with numbers, and we need to be careful that we shouldn't just assume this is going to apply with this new type of product, but we'll show down below that actually this property holds for matrix vector products as well. And the second property here says if I take matrix A and I multiply that by vector CV, so scalar C times vector V, that's equivalent to saying let's first multiply A times vector V, and then we can multiply that resulting vector by scalar C. So this is like a commutative sort of property. We can change the order that we do these operations. So let's take a look at the first property, this distributive property. So why is it that A times the sum of two vectors is equal to the sum of A times the first vector plus A times the second vector? So let's prove this result down below. So let's let A1, A2, AN denote the column vectors of matrix A. So each of these vectors is in Rm because we have m rows and n columns. So each of the n columns is one of these vectors A. Well, then we have A times u plus v. So here I'm going to write matrix A. These are not scalars, right? These are each column vectors in Rm. And we're multiplying this by u plus v. So we're going to say u1, u2 up to un. These are the entries of vector u. v1, v2 up to vn are the entries in vector v. So therefore, the sum u plus v, that would be u1 plus v1, u2 plus v2, and so on. So we want to compute the product of this matrix A times this vector u plus v. So by definition of that product, we would say u1, v1, so we take the first entry times the first column, second entry times the second column, and so on. So here we're just using the definition of what it means to take the product of a matrix and a vector. And so we look at this first term, recall from previous properties that this scalar times A1 can be written as u1 times vector A1 plus v1 times vector A1. And we can do this for every single term in our sum, and then we can regroup all of these terms. So I'm going to group all of the u1, all of the terms that have a u of some sort in it. So I've got u1, a1, u2, a2 from this term, so on. And then we group all of the terms that have some v in them. So from this term, we have v1, a1, v2, a2, and so on. And now each of these is just by definition a product of a matrix and a vector. Right? In particular, this first one is A times vector u, and this second group of terms can be written as the matrix A times the vector v. And so this concludes our proof because we've just shown that A times the sum u plus v is equal to the sum au plus av. And this second property I won't prove in this video, but it actually should follow in a little bit simpler than the first property that we proved. So it would definitely be good practice to try and convince yourself why this second property also holds.